Okay, so to start off, when we're talking about air conditioning, we're talking about boiling and condensing refrigerant. And to get a better understanding of how that works, the first thing that we're going to do here is take a look at a substance that we're all familiar with, and that is water. When it comes to water, if we draw a graph that outlines the temperatures that water changes state at, then we can draw some parallels between that and what happens when refrigerant changes state in an air conditioning system. With water, there's two numbers we're usually pretty familiar with, and that would be the boiling point and the freezing point of water. The temperature that water boils at, 100 degrees Celsius or 212 degrees Fahrenheit. The temperature that water freezes at, be 0 degrees Celsius or 32 degrees Fahrenheit. So these temperatures right here, we're assuming we're talking about the temperatures at sea level, of course. And if I take a look at the difference between boiling and freezing, that's where water is a liquid. And then once it's boiled, it is a vapor. And after it's frozen, it's a solid. The temperature change that we can measure with a thermometer, that temperature change is called sensible temperature. And there is 180 degrees Fahrenheit of change in sensible temperature between freezing and boiling. That's 212 Fahrenheit minus 32 degrees Fahrenheit. The reason I'm using Fahrenheit in this explanation is because heat energy is measured in BTUs. And BTUs is the amount of heat energy necessary to change 1 pound of water 1 degree Fahrenheit. So if I add 1 BTU, and let's assume the amount of water we're talking about here is 1 pound of water. If I add 1 BTU to water in its liquid phase, what happens is it goes up 1 degree. So the amount of BTUs needed to get water from 0 to 100 degrees Celsius or 32 to 212 degrees Fahrenheit is 180 BTUs. Now, if I take that 1 pound of water and I have it in a pot and I bring that pot up to boiling, what'll happen is my thermometer sitting in that water, it's going to get up to the point where the water starts to boil, but then the water doesn't get any hotter than that. It just boils. But assuming that pot's sitting on the stove, the element is still on and we're still adding heat energy to that water and it's busy boiling away until it finally all turns to steam. And then the steam, once that water is all steam, then we can continue to heat it up afterwards. But that point in time where that liquid water was boiling, where we're busy adding heat energy to that water, but not seeing a rise in sensible temperature, that's called the latent heat of vaporization. It's where you're putting heat energy into something, but you're not seeing a change in temperature. That's latent heat. When something's boiling, that right there is the latent heat of vaporization. And something that is quite interesting is it actually takes 970 BTUs to convert that 1 pound of water into 1 pound of steam. It only took 180 BTUs to get the water from freezing to boiling. The point I'm making here is you can soak up a lot more heat energy by getting something to change state than you can by just heating up or cooling down that substance itself. The same thing applies in refrigeration. What we do is we take a liquid refrigerant and we sit there and we kick it back and forth across that latent heat of vaporization point, its boiling point, or its condensation point. And then we can make that refrigerant soak up a whole lot more heat energy than if we just simply warmed up and cooled down a liquid or warmed up and cooled down a vapor. So in the refrigeration system, when we go from a liquid to a vapor, what we're doing is we're soaking up heat energy. That's what happens inside the evaporator. When we go from a vapor to a liquid, we're giving up a lot of heat energy. That's what happens inside the condenser. And one thing that's really important to understand is if you have the refrigerant inside your evaporator go from a liquid to a gas, and all you're doing now is warming up that gas, that's not a very efficient way to transfer heat. Warming up the gas here, if we were using water as our example, if we warm up water vapor past, the 100 degrees Celsius here, again, we're back to that point of just having that, 1 BTU per degree kind of a thing. It's not very efficient. But if you warm up that vapor past the boiling point, that's called superheat. You run the refrigerant through the condenser, and the condenser cools down the refrigerant below its condensation point. We went from a vapor back down to a liquid. That's called subcooling. In any refrigeration system, the critical thing is that we make it across the line, but we don't have excessive amounts of superheat, and we don't need excessive amounts of subcooling. If we stay right at that boiling point, we end up with the most heat transfer happening the most efficiently that we can. One thing to also take note of is with water, using water as our example here, when it goes from a liquid to a solid, when it freezes, it also takes more heat energy for that to happen than just to cool or warm the ice or the water. And that's called the latent heat of fusion. And I think I'm right with my numbers here. I don't know for sure. I think it's 144 BTUs per pound to get across the line there. So you can see that going from a solid to a liquid, there's less latent heat there than going from a liquid to a vapor, but there still is some. So the next thing that we're going to look at here is what happens with, we'll just go down below this one, with an actual refrigeration system. What happens inside of there? And we're going to start off with a simple sketch of the major components, and we'll look at what happens in each area. We're going to start off with the compressor. And our compressor is a pump. The job of the compressor is to raise the pressure of the refrigerant. And another important thing to understand is that the compressor is designed to compress vapors, not liquids. If you run liquid through a compressor, you'll destroy it. So your compressor is going to send the refrigerant down to the next major component in the system, and that's a heat exchanger. Okay, that heat exchanger is designed to reject heat. That's why I've got the arrows pointing out. And then from there, we head on down to the receiver dryer. The receiver dryer on a refrigeration system is it's a device that has a couple of different jobs. One job is to hold liquid refrigerant. Another job is to act as a filter to keep the refrigeration system clean. And a third job is to act as a desiccant to remove moisture from the refrigerant. So that receiver dryer is now going to be sending the refrigerant off to the next major component, which is our expansion valve, which is a variable orifice. That's all it is. That expansion valve sends refrigerant to the other heat exchanger. That heat exchanger is the evaporator, which is designed to soak up heat. So we're going to have the arrows pointing in. And then we're going to come over to the compressor here. So at this point, aside from a couple of other control components, we do have a functioning refrigeration system. Compressor, condenser, evaporator, thermal expansion valve, receiver, dryer. With a system like this, we can divide it up into 4 quadrants. Now these quadrants here, starting with the compressor, we can take a look at what's happening in each area of the refrigeration system in terms of temperature, sensible temperature, okay, in terms of pressure, in terms of BTU content, it's thermal energy, okay, and in terms of the state of the refrigerant. When the refrigerant comes out of the compressor, we raise the pressure on it and the temperature goes up, okay. We have an adiabatic change in the temperature of the refrigerant. This adiabatic heating, what that really means, it's the same thing that happens inside of a diesel engine. When you compress air in the cylinder, the piston moves up. We didn't add external heat. That's not the reason the air got hot. The reason the air got hot is because we compressed it. The same thing happens in your refrigeration system. If you were to feel the suction line going into the compressor and the discharge line coming out of the compressor, you'd find that one's fairly cold and one's fairly hot, even though all that we did was just raise the pressure of the refrigerant. But the reason it does that is because of that adiabatic heating. Adiabatic simply meaning there's a change in sensible temperature without a change in the heat energy in that substance itself. As we move through the condenser, the job of the condenser is to change the state of the refrigerant. And to change the state of the refrigerant, we have to remove some heat energy from the refrigerant. And we're probably going to end up cooling the refrigerant down a little bit as it comes through. So here we have probably high to medium temp, depending on how much we cool the temperature of it down. The pressure is still going to be high. The BTU content at this point, what we've done is we've stripped all of that latent heat of vaporization out of the refrigerant and turned it from a vapor back to a liquid, just like we discussed in our previous diagram with the water. So that means we have low thermal energy. And we've changed the state from vapor to liquid. That liquid is going to carry on through the system and it's going to end up in the receiver dryer and up at the thermal expansion valve. The job of the thermal expansion valve is to reduce the pressure on the refrigerant. When it comes to any substance, whether it's refrigerant or whether it's water or anything else like that, when you change the pressure, you also change the boiling point. If you think about how changing the pressure on something could change the boiling point, a good example of that is how the boiling point of water changes depending on the elevation that you're at. If you're at sea level, then yes, the boiling point of water is 100 degrees Celsius. If you were to go up to the top of Mount Everest, for instance, the atmospheric pressure drops significantly once you're at that altitude, and the boiling point of water is now roughly 70 degrees Celsius. The change in pressure changes the boiling point. The lower the pressure, the lower the boiling point. And just for reference here, if we're talking about 134, the boiling point of 134 at atmospheric pressure is about minus 20 degrees Celsius. Okay. So in the expansion valve, the job of that is to drop the pressure okay. And when I drop the pressure, that also drops the temperature, the sensible temperature. And by dropping the boiling point well down below whatever the ambient air temperature is that we're trying to cool off in terms of cab air, that means it's going to be very easy to transfer thermal energy into the liquid that we have. Because right now, that liquid is still very low BTUs. It hasn't really boiled yet. It's just an atomized liquid that's sprayed out of the TXV. So that liquid goes into the evaporator, and the job of the evaporator is to turn that liquid into a vapor and make sure that, you know, we soak up as much possible heat energy as we can out of the cab air so that we get nice cool air blown inside the cab. And another job of the air conditioning system and the evaporator specifically is to dehumidify the air, and it dehumidifies the air by condensing water on the fins and then letting that drip off and drain out the cab through your drain off hose. So after we get through the evaporator, what we're going to have is still low pressure. Okay, we're still going to have low temp. Now here's the thing, the temperature on the outlet of the evaporator is going to be just slightly warmer than on the inlet, and the reason it's just slightly warmer is because all that liquid that was in there got boiled off, and then just before it exits the evaporator, it's in a vapor state, and we warm that vapor up just a little bit. We try to maintain the correct amount of liquid refrigerant flow going through the evaporator by modulating it with the thermal expansion valve. Something that's really interesting is, even though the pressure and temperature are low, the amount of thermal energy in the refrigerant is now very high because we soaked up BTUs by condensing water and cooling cab air. We soaked up BTUs, and now that refrigerant, even though it's still quite cold, has got a lot of thermal energy in it, and it is now a vapor. And because it went from a liquid to a vapor, that's how we soaked up all that heat energy. That slight amount of heat or of sensible temperature increase, that's called superheat. We need to have a little bit of superheat across the evaporator so that we know if we've got the evaporator full of refrigerant, whether we're flooding it or whether we're starving it. And the way that that works is we put a temperature sensing bulb on the outlet line of the evaporator, and we run that bulb back to the expansion valve. So here's what happens. That temperature sensing bulb is, it's actually filled with the same refrigerant as what's in the system. But without getting into that too much, the whole idea of this is that the bulb itself senses the outlet temperature of the evaporator. And if the outlet temp of the evaporator is too warm, that means that we were warming up too much vapor. That means there wasn't enough liquid in the evaporator to keep it cool, keep it full, and soak up heat energy. If the amount of superheat is not enough, that means that we're flooding the evaporator with liquid and we're not warming up any liquid at the end before it gets out. And if that happens, we might end up with liquid exiting the evaporator and then getting into the compressor and destroying the compressor. So the job of the sense bulb on your thermal expansion valve is to measure the outlet temperature of the evaporator and use that information to throttle the inlet flow of liquid. That's the job of the expansion valve. And to do that, it usually maintains, maybe 5 or 10 degrees of superheat across the evaporator. Too much? That means we don't have enough refrigerant, so it opens up. If there's not enough superheat, that means we've got too much refrigerant going in, things are staying too cold, so we start throttling it back some. Another term that we did talk about was subcooling. As the refrigerant goes through the condenser and that vapor turns into a liquid and we cool that liquid off a little bit, the drop in temperature on the outlet of the condenser versus the inlet, that's your subcooling. Now, as long as you have some, that's really all you need. If you have some subcooling, that tells you that phase change took place, you're golden. There's no specific amount you have to have, you just have to have some. When we're talking in generalized terms here for mobile air conditioning. So anytime you get a refrigeration system, you're also going to have service ports. And those service ports let you hook your manifold gauges up. Your manifold gauges, you measure your high side and your low side with them. And the pressures that you see on those, there's a couple of different numbers that you should be aware of. But in general, your low side, and here we're talking specifically about 134, under most operating conditions, we're going to be between roughly 10 and 30 PSI if the compressor is running. On the high side, the pressure is going to vary quite a bit depending on the heat load on the system. The higher the heat load, the higher the high side pressure. And heat load is the only thing that dictates high side pressure. There's a few exceptions to that, but under normal operation, high side pressures, there's no way to give you a firm number as to what your high side pressure is going to be because it varies. It can vary easily anywhere between about 150 and 350 PSI. If your air conditioning system is operating and it's really cool outside, you might even see lower numbers than 150. If it's really hot outside, maybe they'd get higher than 350 depending on how well everything else is working. Now, to make sure that we don't damage the system, we're going to put pressure switches in the system. Most systems have a pressure switch at least on the outlet. Some of them have one on the inlet to the compressor. But if there's only one switch and it's on the outlet, that means it's a high-low switch. Okay, and that means that it usually cuts out somewhere around 0 to 5 PSI on the low end. Okay, if we get back above that, it'll cut in. And then on the high end, if the pressure gets too high on the outlet of the compressor, and that's usually somewhere between about 400 and 450, depending on the system, it's going to cut out again at the high end. So protect the system from overpressure at the high end if there's something wrong with the system and the compressor needs to shut off, or protect the system on the low end if it's so cold that the static pressure on the refrigerant is down to levels where it's not safe to run the compressor anymore, or if the system is empty, there's no refrigerant in it. The reason we don't want to run the compressor when there's no pressure in the system is because the refrigerant carries the lubricant for the compressor with it. The compressor is lubricated much like a two-stroke gas engine, where instead of gas and oil, you've got refrigerant that has the oil dissolved in it, and that carries it around through the compressor to keep the compressor lubricated. So when we're operating a system like this, if everything is working normally, my high side pressure is going to vary depending on what the ambient temperature is and the heat load on the system is. My low side, generally it's going to be sitting between about 10 and 30, depending on what's happening with the system, but somewhere in that neighborhood. So now that we know how the system is supposed to work, let's talk about what happens when it's not working correctly. Some common problems that can happen with the air conditioning system. Probably one of the most common problems is a low charge. When I got a low charge in the system, that means there's not enough liquid in the system to keep everything full of liquid that needs to stay full of liquid, specifically the evaporator. If I got a low charge, then what will happen is the thermal expansion valve is probably going to be wide open. And because we don't have enough liquid, and the receiver dryer should be full of liquid. In fact, we should be full of liquid all the way to, say, roughly the bottom of the condenser, so that we can have the correct amount of liquid flow going through the system to keep the evaporator as full as it needs to be. If the evaporator is starving for liquid, that means that we're going to have excessive superheat. The outlet line of the evaporator is going to feel warm. And if the outlet of the evaporator feels warm and the inlet feels cold, that right there is a classic sign that you got a low charge. Another thing that'll tend to happen is the compressor is going to be pulling refrigerant through. It's not liquid pressure feeding anymore. The compressor is actually trying to suck liquid that's just not there. It's trying to suck vapor that's not being produced because there's no liquid. So what happens? Well, first of all, the expansion valve's wide open. And secondly, when the compressor is pulling down the pressure, if it has what a lot of systems nowadays are supposed to have, or starting to have, I should say, if it has the low side switch on this side and not built into the high side switch, if it has a separate low side switch, what will happen is that low side switch, it'll cut the compressor off as that pressure drops down. So you're going to end up with constant compressor cycling. As soon as that compressor cuts out, expansion valve's wide open, and the pressures on the low side and the high side, they're going to start to equalize quite quickly, and that means the compressor is going to kick back on right away. When your pressure equalizes quickly and your compressor cycling on and off, you got lots of superheat. And poor cab cooling, those are all classic signs of a low charge. All right. And when you got a low charge, you may have normal or low static pressures. Okay, when we're talking about static pressures, we're talking about what are your high and low gauges reading when you first walk up to a machine and you clip your gauges on and just see what pressures in the air conditioning system. If your pressures are appropriate, all that means is there's some liquid in the system. It doesn't necessarily mean there's enough liquid in the system. Static pressure is developed because when it comes to refrigerant, and you have that refrigerant in an enclosed container, and you put a gauge on it, if there's any refrigerant in that enclosed container, your gauge is going to read some pressure because ambient temperature put heat energy into that container. The refrigerant boiled and it turned into vapor, and that vapor builds a certain amount of pressure. And once the pressure builds up to the point where the pressure temperature relationship gets to what's called a saturated pressure, now the refrigerant stops boiling, the pressure stops rising, and you end up with static or saturated pressure. Now with 134, it's roughly 70-70. So at 70 degrees Fahrenheit, you should have about 70 PSI. I think the actual number is like 71 point something, but 70-70 is really easy to remember. Okay. So a comfortable room temperature, you should have about 70 PSI of pressure in your refrigeration system. And it doesn't matter if that refrigeration system is completely full of liquid or if there's only a few ounces of liquid left. As soon as that liquid is boiled off enough to build the pressure, if there was enough liquid to make that happen, it'll hit your static pressures. If there was not enough liquid to make that happen, all of the liquid boils off, and then your static pressure is lower. Just because you got the right static pressures doesn't mean you've got a full system. Now, lack of airflow across a condenser. So low charge or poor airflow across your heat exchangers. Those are the things that tend to usually go wrong with air conditioning systems. And if you think about things like agricultural equipment and heavy duty equipment where they tend to work in very dirty, dusty environments, a lack of airflow across a condenser can absolutely happen. And if you have a lack of airflow across the condenser, what you may end up with is the system works for a little bit at first, and then your performance falls on its face or it shuts off entirely. Okay. And when that happens, you'll notice that your pressures on your gauges, you're going to have excessive high side pressure. Okay. You're going to have poor cooling. And no subcooling. You may end up with the compressor shutting off. And the reason the compressor shuts off is because as the refrigerant is exiting the compressor and trying to get through the condenser and do what it's supposed to do, no airflow goes through the condenser, so we're not removing all of the heat energy from the refrigerant. And if we don't get the heat energy out of the refrigerant, we don't turn it into a liquid. And if we can't turn it into a liquid, it's still a gas when it gets into the receiver dryer. The other thing is heat load dictates high side pressure. And if we're not getting rid of the BTUs in the refrigerant on the high side because the condenser is plugged, that means the heat load is still effectively quite high and your high side pressure starts to rise. And it gets to be way higher than what it should be for the ambient temp that system's operating in. And if that's the case, you're going to see your high side pressure spike, maybe even kick out the high cutout switch, and your compressor shuts off. And it won't turn back on until the temperature comes back down. So when you got a problem like this, check and see if you got airflow through your condenser. Check and see if you got any subcooling. Another thing you may notice, if there's a sight glass on the receiver dryer, you're going to see bubbles in there. Another very common problem is air in the system. So if you have a low charge, your static pressures are probably going to be low, maybe normal. If you got a lack of airflow across the condenser, but that was really the only problem with the system, your static pressures are going to be normal. If you have air in the system, your static pressures are going to be high. Your static pressures are high because air and refrigerant do not mix together. If you got air and refrigerant in the same container, whether that container be your refrigerant recovery bottle or the air conditioning system on a machine, the air and the refrigerant won't mix, and that drives the pressure up in the system. When you try to run the system, you're going to have poor cooling performance, and you're going to notice that your high side pressures are way higher than what they should be. Your high side pressures being higher than normal, what might happen there is we may end up with the high switch cutting out as well. You're going to have poor cooling performance. And if you're trying to figure out if you got air in the system or if it's some other problem with the system, air in the system is pretty easy to identify as long as you remember to check your static pressures when you start. But here's a real question. How does air get into the system? Well, air gets into the system in the wintertime. So here's your air conditioning system. Okay, and I'm just drawing this as a container of refrigerant. Okay, and that container of refrigerant is going to have some liquid in it. And the pressure on that container of refrigerant is going to change based on the ambient temperature that that container of refrigerant is sitting in. So if I take that container of refrigerant and I stick it outside and it's 20 below outside, remember what I said, at 20 below, the pressure is going to go all the way down to 0 psi. That's the boiling point at atmospheric. But if I was to take that same tank of refrigerant and cool it down below 20 below, let's say it gets down to 30, 35 below outside, that means that I end up in a vacuum inside that container because the refrigerant has collapsed down below its boiling point. That means it's actually in a vacuum. And if you have any leaks in your AC system, that vacuum is going to start pulling air into the system. So you got a problem that happens over the winter, but you don't know it happened until you try to use that AC system in the spring. Here's another one. And this is one that usually happens because of an inexperienced person trying to service an air conditioning system and not really understanding how it works. All they think is if it's not working properly, it probably just needs more refrigerant. So they head on down to their trusty parts store, grab a can or two of Redtech or Duracool, slap it in there, and it still doesn't work. Okay, or maybe they got access to 134, so they go and try and add some refrigerant to it. Let's top it up. Well, that's stuff you're not allowed to do anyways. But if somehow you end up overcharging a system, then what'll happen is you're going to end up with normal static pressures, but during operation, your high side is going to be higher than normal. Okay. Now, when you have air in the system or an overcharge, the system might cut out at high pressure. And the reason for that is the high side switch is protecting the system. So the way the systems react, if it's air or if it's an overcharge, can be fairly similar. The reason an overcharge drives up your high side pressures is because if you take a look at your evaporator, sorry, not your evaporator. Oh. If you take a look at your condenser, if I put too much refrigerant in the system, then instead of the condenser being full of liquid to just the very bottom of it where it should be, it actually ends up full of liquid almost all the way through. Now my condenser is full of liquid. That means I have less actual active surface area in the condenser for it to be a condenser. It can't get the heat out of the system like it should be. And that means I end up with too much heat load in the system. Too much heat load in the system drives my high side pressures up, causes it to kick out, which when the system is running, actually looks fairly similar to what happens when you got air in the system. The way you tell if it's air or an overcharge that's making this happen is by looking at your static pressures. Okay. One other thing that can happen with an air conditioning system is moisture in the system. And moisture in the system and a plugged expansion valve, they do look fairly similar. So we'll look at both of those together. Moisture in the system. If you got moisture in the system and your desiccant is fully saturated in your receiver dryer, that moisture is going to want to start to freeze into ice inside the system. And that ice is probably going to happen right where things start to get cold, near your expansion valve. If you got enough moisture in the system, that expansion valve can freeze up and now you have no refrigerant flow in the system. So what'll happen is your AC system works for a bit and then it stops. And then if you wait long enough, it'll start working for a bit again. If it's a plugged expansion valve, it's probably not going to work at all. Okay, but in both cases, your static pressures will look normal. In both cases, your low side pressure is just going to pull down and then your compressor kicks off. Okay, your gauges will not equalize quickly And the reason the gauges don't equalize quickly is because there's no flow across the expansion valve. If it takes a really long time for them to equalize, chances are the expansion valve is plugged with moisture. If they just pull apart and stay there, or they equalize very, very slowly, and they're always doing that, it's probably a plugged expansion valve. If you got a restricted expansion valve, not 100% plugged off, it'll pull down and it'll slowly come back up. Compressor kicks on for a bit, AC works, just a brief blast of cold, and same thing happens over and over. When it comes to troubleshooting different problems with the AC systems, the first thing you always want to do is check your static pressures, and then get your gauges on and check and see what your operating pressures are. The other thing you want to do is you want to get access to the evaporator and the condenser so that you can feel or measure with infrared temp gun the superheat and subcool, because again, that tells you a lot about what's going on with the system. There's other problems that can happen with the air conditioning system, but these ones that we've looked at here are some of the more common problems. In the next lesson that we do, we're going to talk about how to use the equipment, the manifold gauge sets, your recovery, your vacuum pump, your recovery machine, your vacuum pump, some leak testing things. We'll talk about how we use all of that to troubleshoot and how we use it to repair the system as well. We'll deal with that in the next video though. So for now, we are done with this one.